Bridges by Rachel Thompson. In this engineering technology class, we discuss the 9 main core technologies that are present all around us. Among these are materials, mechanical, electrical, electronic, structural, fluid, optical, thermal, and biotechnology. While I'd love to explain all these technologies, I'm afraid that only 2 are relevant to this project. Materials technology, the production, changing, combination of materials, and structural technology, the putting together of items in order to build structural supports, are the other ones relevant. The bridge was an example of structural technology because you're putting together small pieces of wood in order to create a bridge that will essentially stand weight. On these bridges, 4 forces can constantly act upon it, enticing it to collapse. These 4 forces are tension, compression, torsion, and shear. Tension is the force of pulling the bridge in 2 separate directions. It normally occurs in cables of certain bridges along with certain diagonals. Compression, unlike tension, is the force that pushes the bridge in the same direction. It often affects the top and certain diagonals of a bridge. Unlike tension and compression, torsion and shear aren't as common among bridges. The force of shear occurs when 2 conjoined pieces are separated, while torsion is the twisting motion of a bridge. While you're driving or walking around town, you often see bridges all around you. Among these are the beam bridge, the most simple among the bridges, the arch bridge, the suspension bridge, and the cantilever bridge. On a beam bridge, tension affects the bottom while compression affects the top of the bridge. On the arch bridge, compression affects the actual arch of the bridge while tension occurs in the cables. The suspension bridge mostly undergoes the forces of tension and torsion, which both occur in the cables. Compression is only present in the long towers. Much like the beam bridge, the cantilever bridge undergoes compression on the upper members of the bridge, while tension occurs on the bottom. While some of these bridges seem indistinguishable compared to others, there are 2 ways to tell them apart. One of these ways is by the 3 types of trusses: the Warren, the Pratt, and the Howe truss. These trusses are all arranged differently, making them easily distinguishable from one another. The Warren truss is a collection of triangles that alternate in direction. Compression and tension also alternate between the diagonals. Tension affects the top of the bridge, while compression affects the bottom. The Howe truss is a collection of half triangles separated by straight bars. The triangles face to either the left or the right. The triangles on the left as well as on the right undergo compression, while the straight bars that separate them undergo tension. Compression affects the top of the bridge, while tension affects the bottom. The Pratt truss is distinguished by the many differently placed triangles present. First, on the far left is a full triangle separated by a strong tower. Following that is a half triangle pointing to the right. Followed by that is a full triangle, yet again separated by a tower. Then, following that one, is another half triangle, facing to the left this time. Then, it is followed again by another full triangle. Compression and tension are the exact opposite of the Howe truss. Tension is labeled in red, while compression is labeled in blue. Another way to distinguish a bridge will be the type of roadway configuration it has. Among these are the deck, the pony, and the through roadway configuration. The deck roadway configuration is when a vehicle drives on top of the bridge or the structure. The pony roadway configuration allows the vehicle to travel through the bridge, however, said bridge has no top to it. The through roadway configuration is different than the others. It allows vehicles to travel through the structure, however, unlike the pony, the roadway configuration has a top to the bridge. Now that you know about all the bridges and their trusses, it is now time to begin designing. When designing the bridge, there are many things you have to think about. How could I make a bridge that was relatively easy to build and make it efficient as well? How could I design a bridge that was low in cost and could get me a good score on the testing process? With these questions in mind, I later decided to build a Warren Truss bridge, seeing that it was the easiest for me to recognize and build. While on West Point bridge design, I fiddled around with the many types of beams that could be used, seeing how each setting affected the efficiency of the bridge. It was then when I discovered that hollow tubes, when in compression, are just as effective as solid tubes. With the new knowledge under my belt, I was able to effectively design a bridge within a few days. After the designing process was completed, I then began transferring the drawing over to Vectorworks in order for it to be built. I used the fraction 13/24 equals x over 6. 13 was the required length of the bridge, 13 inches that is. 24 was the number that was given on West Point Bridge Design, which was the length of the bridge to begin with. X was the height that I needed to figure out, and 6 was what x was over in order for me to figure out what to multiply it by to figure out the proportion. While designing and building this bridge may be a tedious task, there are many ways to get over this as quick as possible. First of all, do not waste any time that you have working on it. Make sure you are very efficient with your work habits, otherwise you'll be pressed for time later on. While working hard on doing your best to get this done, also make sure that the bridge you're going to build is actually possible. Keep in mind, the bridge that you design is the one you have to build in the future. After a long, tedious effort of building my bridge, it was finally time to test it by showing how much force it could take before finally breaking. The test would start off with 3 people, one being yourself, another being your partner, recording the breaking of the bridge, and the last being Mr. Maloney, giving you the signal to raise the lever that would then apply the force to begin breaking it. However, before that, there were other things you had to do. Before you have your bridge tested, it must be weighed and a picture must be taken. The weight that you get is the unloaded weight of the bridge. Then it's time for the actual test to begin. This is when you, or the other person that's breaking the bridge, are going to lift up the wood block that is connected to a device that records force. You or the other person will continue to lift up the block until the bridge finally breaks.
So Demetri, are you ready?
Yes.
Lift up. Lift up, faster. Good one. Wow. Nice. That was a cool one, see? Bam! Broke it 41-31. That was pretty good.
41-31.
41-31.